it's the sort of thing, like, if the world of math works out nicely, this should just be true, and it is true, and this is just like a math proof. There's not really quantum content in what I'm going to do, but there's some geometry content, I suppose, so we'll do it. Okay, so the last thing we need to sort of show about planes of rotation is that, okay, these planes that we found are perpendicular to each other. In other words, so let's pick two of them. We'll call them the theta1 plane, which is like k1 over L times tau. It would be nice to have just a simple symbol, theta1, for it. And theta2, which is k2 over L times tau. And we also need that they're not the same. Okay, so we picked two different planes. Okay, then let's say SW theta1 and SW theta2 are perpendicular. Now, actually, that's not all we need to show, because this is just one of the two basis vectors for this plane, and this is one of the two basis vectors for this plane. So really, we need to show SW is perpendicular, and also if you were to write a perp here and or to write a perp here, all four of these possibilities are perpendicular. But I'm just going to show it without any of the perps, and the proof is basically the same in the other cases, and a case of it is on homework, so I hope you'll judge that that's sufficient. Okay, so I'm just going to show that these two basic ones are perpendicular. And, how do we show things are perpendicular? The easiest way is to compute the dot product and show that it's 0. So, i.e., have dot product 0. Okay, if we were being cool, math, quantum people, we'd write it this. That's just the dot product, but we won't do that. We'll just think about the dot product in the usual way, where you multiply the coordinates and add them up. Okay. Okay, so we're going to be dot producting two vectors that look like this, but have different amounts of angle by which they change. And how do you dot product things? Well, imagine, I'm not going to do it, but imagine we're dot producting this and this. Then it's well, we multiply these two numbers and these two numbers and add that, and also multiply these two numbers and these two numbers and add that, and also these two and these two and add that. So it's you kind of take all the little 2D vector dot products and add those up. Actually, we're going to talk about averaging those up. Actually, as long as you're checking whether a number is 0 or not, it doesn't matter if you take the sum or the average. Actually, in some sense, there's another natural reason why the average comes up, which is, you might remember last time, or might not, that we looked at the unit length version of these. Okay, so these are actually unnormalized states, and we computed last time that their squared length is L. The dot product of the steering wheel state with itself is L, which means its length is square root L, which means that if you wanted a unit length version, you'd have to multiply by square root of 1 over L. Okay, so we might just take the dot product of the unit length vectors of these things and check that that's 0. It's the same thing. And that's nice because if we do that and we say, I'm going to look at the dot product of the unit length versions, so their dot product is, well, it's the same as taking the dot product of these two, but then you get an extra factor of 1 over L. And that's kind of pleasant even, right? Because that turns this overall sum into an average. So it doesn't really matter, because we're just trying to check that it's 0 anyway, so it doesn't matter if we multiply by 1 over L or not. But it'll be nice to say this, that their dot product is the average of all the associated I don't know, 2D vector dot products. Okay, so we're trying to show that this average dot product is 0. So let me write that. Okay. So this is going to be like a math trick, a math thing. So indeed, you know, if you had SW theta 1 here and SW theta 2 here, like some general dot product, this dot product of this vector with this vector, there's a simpler way to think about it because, you see, this is the dot product of 2 unit vectors in 2 dimensions. So what does the dot product mean, or what is one meaning of the dot product for 2 unit vectors? It's related to the angle between the vectors. It's the cosine of the angle between the vectors. Okay, so let me write that as well. Each 2D dot product, I wrote dot too many times, is like cosine of theta, where theta is the angle difference between the 2 vectors. Okay. So actually, I kept pointing over here, so let me just write over here. So let's say this one is theta 1, and this one is theta 2. I guess then we have to slightly adjust this picture. This is theta 1, and here it's also going to start horizontally, but it'll go by theta 2s. So maybe, I don't know, maybe this is theta 2, and this is 2 times theta 2, and so forth. Okay, well, I guess it's kind of easy to see for each of the little 2D vectors what the angle difference is. The first angle difference is 0. And then the second angle difference is like theta 2 minus theta 1. And the third angle difference is like 2 theta 2 minus 2 theta 1, and so forth. So the angle differences are 0, theta 2 minus theta 1, 2 times theta 2 minus theta 1, 3 times theta 2 minus theta 1, and so forth. There's a L total thing, so the last one is like L minus 1, theta 2 minus theta 1. Okay. And so let's make a notation for this. Let capital delta be theta 2 minus theta 1, this angle difference. And while we're talking about theta 2 minus theta 1, let's make a couple of observations about it. Well, this is theta 2 and theta 1. So actually, theta 2 minus theta 1 is k2 minus k1 over L times tau. Okay, so this is like integer over L times 360 degrees. That's one thing that we can say. So it's like a fraction of L of the circle. So it's another one of these angles which has the property, if you like rotate by delta, 2 delta, 3 delta, 4 delta, L times, you eventually get back to 0. You'll wrap around integer many times in doing so. And another key fact about it is it's not 0. And it's not 0 because theta 2 does not equal theta 1 because these are different planes of rotation. Okay, so good. So these are the angle differences. So the dot products that we're averaging are the cosines of these. So the dot products being averaged are cosine of 0, cosine of 1 delta, cosine of 2 delta, dot, 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 cosine of L minus 1 delta. Okay, so all these things are like average of like a bunch of cosines of angles, which seems a little scary. We're supposed to show that this average is 0. But it's true, and there's like a little math trick for this too. I don't know if you've ever seen this trick in your life, but I'll show it to you. So at this point, you can actually forget how we got here and just be like, all right, the very last thing we need to do is like yet another math trick. We need to show that, you know, if delta looks like this, it's like an integer fraction of L of a circle, and you average up cosine of 0 delta, 1 delta, 2 delta, up to L minus 1 delta, you get 0. Okay, so that's the math fact. And if we prove this, then we're done with everything we were trying to do, this want to show about the planes of rotation being perpendicular. Okay, so the trick to this is the following. So clear your mind and forget everything we were doing and just imagine you're trying to prove this fact about averages of numbers. Now I'll do another little trick, which is like a cool way to compute this average. So the trick is this, like draw a circle in 2 dimensions, the unit circle. Not the greatest circle, but okay. This is the unit circle in 2 dimensions. And just consider the points or the vectors, the L unit vectors whose angles are these delta things. 0 delta, 1 delta, 2 delta, up to L minus 1 delta. Okay, so I'll draw them over here. So this is the one at angle, maybe delta, and then maybe this is the one at angle, okay, let me draw it. 2 delta, maybe this is the one at angle 3 delta, right, 1 delta, 2 delta, 3 delta, 4 delta. Okay, maybe in this picture delta is 5. Or sorry, 5 over, sorry, 1 over L. 1/5 of a circle. It took me several tries to get that. So maybe I shouldn't even done like 1/5 of the circle because maybe it's like too simple a case. Like you could do like 2/5 of the circle, let's say, just to illustrate it. Let's say delta is 2 over 5 tau and L is 5. So then we go like, this would be like 0 delta, and then this would be 1 delta, and then this would be 2 delta, and then this would be 3 delta, and then this would be 4 delta, and then we'd be back to it at 5 delta. Okay, that one's maybe better because it's not just like it ticks around, but it like wraps around multiple times. It illustrates the point. But the point is, like once you get up to like L delta, because delta has an L in the denominator, you get like an integer number of wraparounds of the circle, so you come back to where you started. Okay, so they're tips. These dots that I drew as dots, these are equally spaced around the circle. Let me not draw a picture because it looks like 0. And that uses, on one hand, it uses that like, okay, there are L of them, and this fraction looks like integer over L times tau. And it also uses that this angle is not 0. Should have done it like this. This angle is not 0. Because if this angle were 0, like it would be like 0, 0, 0, 0, 0, L times. And like all the dots would be here, and they would not be equally spaced around the circle. But as long as it's not 0, then like you do wrap around the circle some integer number of times that's not 0, and they're equally spaced. Okay. So that means that their center of mass, or like their 2D average, but let's say center of mass, imagine them as little like point masses, is the origin. Okay, so they're equally spaced around the circle. If you imagine this is a disk and their point masses, like it would really exactly balance with the fulcrum at the origin. Okay, so that means if you average up these the two coordinates of each of these vectors, you get 0. So in particular, it means the average of their x values is 0. Their x coordinates. And also, incidentally, we're not going to need this, but the average of their y coordinates is also 0. In fact, these two statements together are precisely saying this, that the average, the barycenter, the center of mass of all these points is the origin, 0, 0. That's exactly equivalent to these two facts. We only need this one, though. Why do we only need that one? Yeah. Yeah, exactly. What are the x-coordinates of these points? Well, the x-coordinate of a point at angle 3 delta is cosine 3 delta. So the x-coordinates are cosine of 0 delta, cosine of 1 delta, cosine of 2 delta, 3 delta, 4 delta. So we're done. These values are the x-coordinates, so their average is 0. So I can just summarize by putting a check mark here. This equals 0. So it also means the average of all the sines of these angles is also 0. But we don't need that. OK. Any questions about this? OK. So that's good. That's the last fact we needed to fully 100%, like 1,000% understand the planes of rotation of this like R operator that we're using for rotation estimation. So we did it. We got all the angles. There are all the angles that look like this. They're perpendicular, everything. Perfect. We found it.